Okay, here we go. Take two. Simple harmonic motion. If you have not printed this out yet from the Google Classroom, then print it out first so you can follow along. If you, for some reason, cannot print it, let me know and I will bring you one. I will drop one off from 6 feet away because that is what the CDC recommends. Okay, Hooke's law. If a spring is attached, if a string is stretched or compressed a small distance, enough that you don't distort this metal, from its equilibrium position and then released, it exerts a restoring force on an object attached to it. So what we're gonna do is we're gonna talk about these various positions of this mass attached to a spring. So I have one thing I need you to do is take a ruler and you're gonna draw a very special little line right here. And let's see, who remembers the name of this line? Angie, go ahead. Oh, that's really not the right answer, Angie. Oh, I'm sorry, would you say? Oh, equilibrium. Yes, that is the right answer. Good job. So then, this is off to the right. We've pulled it and displaced it from the equilibrium position, okay? So now that it's over to the right, my position, my x, is at a positive, and it's to the right, right? It's not gonna go any farther than that, so we're gonna call that a maximum. My velocity, although obviously I haven't really let go of it, but when I do let go of it and it goes back and forth, when it comes back to this position, which it will, this is harmonic motion, when it gets back here, its velocity will be 0, right? It'll be chilling over there. All the way out on the right, it is being pulled which direction by the spring? To the left. And so that's a negative force that is applying, right? That's my restoring force, negative to the left. My acceleration, F equals ma, is proportional to my force. So my acceleration will also be to the left, negative. And that's gonna be a minimum, right? That's a minimum when we graph this, and that'll make more sense. And you'll be like, oh my God, oh my God. As the mass passes through the equilibrium position, right? And again, this is oscillating back and forth. And we're catching it, we're taking a snapshot as it passes through equilibrium. Its displacement is 0, right? It hasn't gone anywhere right or left at this exact moment, it's in the middle. Its velocity, if we want to take a picture of its velocity real fast, a snapshot, it's going in the negative direction and it's moving pretty quickly. And this is a, for lack of a better term, maximum velocity in the negative direction. So we're going to term that a minimum. And the spring is not stretched right now. It's going to be in a moment. It's not stretched or compressed, but as the mass passes through equilibrium, the spring is where it ordinarily would be. And so my acceleration is also 0 because I have no force on it. As it slides all the way to the left, it squashes, stops for just one brief second before it comes back. A brief moment in time. It is now at a negative x displacement right here. So this negative displacement we're going to have as it is off to the left, and it is negative. And that's as far as it's going to go in that direction. So that's going to we're going to call that a minimum. Its velocity, again, as it comes all the way out, it stops for a brief moment in time before it comes back. And so that's a 0 velocity. And my restoring force is in the positive direction. And so my acceleration, proportional to that, is also in the positive direction. That's as far as that spring is going to get compressed. So we're going to call that a maximum. Any questions? Good. Okay. This is Hooke's law. Force of spring equals kx. All right, spring force, spring constant, and displacement from equilibrium. This is how stretchy or squashy a spring is, just like from energy 1/2 kx squared. And this is also just like from energy 1/2 kx squared, the displacement. A stretchier spring has more force, and the farther you stretch a spring has more force. Sometimes you'll see a negative sign in front showing that the restoring force is always opposite, in front of the k, sorry. Sometimes you'll see a negative sign in front of the k, showing that the restoring force is always opposite the direction of displacement. If I pull to the right, the spring fights me to the left, and vice versa. This is just kind of the explanation of the basic idea that x equals negative a and ax equals a. My displacement is my amplitude, right? If we're talking about wave fundamentals and you have notes titled wave fundamentals, that x is, the other way to look at it is amplitude. All right, next page. This is the period of a spring or a simple harmonic motion, right? It takes a certain amount of time to go back and forth. Whoosh, 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 right? That's the period. Period is inverse to frequency, which we know. And we said earlier that our thing that we keep track of for period is the time it takes an object to do one complete cycle of motion. So highlight that right there. Often when we're doing these, we'll make a mistake and not realize that it has to come back to where it started, and we'll get essentially a crest to trough as a frequency or a period instead of a crest to crest. So you always want, it doesn't have to be crest to crest, but it has to come back to where it started from. So if you start at a crest, you have to take the full cycle all the way to the next crest. Or if you start at a trough, you have to take a full cycle all the way to the next trough. Okay, so these, they love these. These are important, so let's pay attention to this here. So period of mass in a spring. If we look at this equation, the period of a mass spring system, all right, M is the mass, K is a spring constant. So is there a G in there anywhere? No, there isn't. So smart. So this is unaffected by gravity. A mass spring system is unaffected by gravity. It is, however, and cross this out here and put a mass over here, printed incorrectly, mass. It is, however, affected by mass. A pendulum, which we'll do in class if we ever go back to school, is like a pendulum in a clock, right? Tick tock, tick tock, tick tock. The period of pendulum, is there a G in here somewhere? Oh, there is. There's G. So it is affected by gravity, but it is, I don't see an M in there anywhere, unaffected by mass. And I'll do a demo again. Next time we're in school, I'll do a demo with this that'll show this concept to you that you'll remember forever and ever because it's fun. Okay. Last piece, my friends, position and velocity. So we're going to graph these. Constant acceleration equations don't apply. That means your kinematics, are not going to let you find the acceleration that you need, right? Again, I'll say that again. Your kinematics, VF squared equals VS squared plus 2A delta X, that's not going to apply because your acceleration is changing. And this is the only exception to the rule in this course where acceleration is a constant. Acceleration changes, and we're going to show you how that works. Okay, so first off, we're going to graph these guys right here. The ones you just said. So back to your first sheet, and we're going to label these little guys. Right? We're going to label them nice and pretty. Oh, here's the one I had for you. There you go. Nice and pretty. So when we label these, we're going to label them as, this is my 0 position. This is where we're starting. Right? My next position, I'm going in a circle. So think of your pi circle, right, from piston. As it goes in a full circle, it comes all the way back around to 2 pi eventually because it's harmonic. It's periodic. Right? The first check-in point is usually pi over 2. My second check-in point is pi. My third check-in point would be 3 pi over 2. Right? In this case, it's periodic, so this kind of does both jobs in a way. Now, it's not completely true. The velocity will be changing as it comes back through going the other way, but we're going to represent that with our graphs. Okay, so with this in mind, right, starting at 0, pi over 2, pi. Let's graph. All right, so what is my position? I have that other guy right next to you, so you're looking at it. What is my, in fact, tell you what, let me put this up here. Can I do that? Where y'all can see that? Yeah. Okay, what's my position at 0? It's a maximum, right? So we're gonna graph this maximum right here. Boom, right? These graphs say pi over 2. At pi over 2, this poor little guy is at 0 for my position, right? Again, this is position, and I'm graphing position. So 0 at pi over 2, 0, pi over 2, so I graph that as a 0. At pi, we're at a negative minimum. At pi, we're at a negative minimum. As we come back through 3 pi over 2, we're coming back through position 0, right? So we're coming back through position 0, and then we'll end up back at a maximum position displaced all the way to the side. Okay, so we'll put a smooth curve on that. We'll try at least. Ooh, all right, it's not bad, huh? Okay, next, velocity. So slide that over to the side, and we're graphing velocity as a function of position, not position, but like oscillation. So we'll start with velocity equals 0. Right? My velocity is 0 at position 1. As it slides through the middle, it is now a negative minimum, right? I guess minimum is negative by definition, as it slides through, but that's as far as it's going to go. That's as fast as it's going to get going in that direction. It comes all the way out to the end, all right? And so at position pi, it's going to be stopped, right? It has stopped. And so position pi, my velocity is 0. So we plot that as a 0. It comes back through the middle, and that's not here. That's 3 pi over 2. It looks like this, but it's instead of going to the left, it's now coming to the right. So as it comes to the right, all right, my velocity is a it's a maximum, all right, in the positive direction because it's flying really fast to the right. So we're going to plot that maximum. And then it goes all the way back out to here where we started. That completes our cycle. We're at 2 pi, and it's holding and waiting to come back. So then we're going to graph.
Finish
now. And it comes through right there. So, as you can see, this guy, right? Periodic function. Oh, they're starting to look familiar, aren't they? Aren't they? Okay. Next, acceleration. Let's graph our acceleration. And acceleration is right down here, over here, and here. So we're graphing these two right here. So, my acceleration at my initial place is a minimum, right? It's a 0. I'm sorry, it's a minimum, my bad, I said 0. It's a minimum, and it's in the negative direction, and it's pulling to the left. As it passes through the center, my acceleration is 0, right? So as it passes through pi over 2, that's a 0. As it gets all the way out to the left side, right? It's all the way on the left side at pi. It's getting ready to fly back. It's a maximum acceleration, and that's positive. So that's at pi, we have a maximum acceleration there. You can see what this is going to look like. As it comes back through the middle, it's a 0 acceleration again. And then when it gets all the way back out to our initial position, 0 and 2 pi, it's a negative acceleration as that spring is pulling to the left hard. Okay, and let's put a curve on that bad doggy. There we go. Okay. And last but not least, energy. Energy is a function of what? Let's see, we'll pick on someone I haven't talked to yet. Karam. Energy in this case is a function of gravity. Good, it is not a function of gravity. Is it a function of how fast it's moving? Yes, it is a function of how fast it's moving, right? And you could make an argument that it is a function of spring, and we'll talk about that difference. And you'd have to specify which type of energy this is. So for now, we're going to say this is kinetic energy, right? And we're going to say what that's going to look like, and then I'm going to adjust it in a minute. So if we're saying this is kinetic energy, right? My kinetic energy is going to be maximum when my velocity is at absolute value maximum. So 0 is 0, right? These two are the same. When this is at a negative velocity, my equation for kinetic energy is 1/2 mv squared, right? So I don't care about the sign on that v. I only care about its magnitude, essentially. So as it comes up here, it has a lot of energy, right? I don't care which direction it is. Energy doesn't have a direction. Energy is energy, right? So all of my maximums and minimums are both going to represent these two this maximum, this minimum, are going to represent a high amount of energy, right? It's in the negative direction, yes, but that doesn't matter. There we go. Okay. Now, for those of you who have paid attention to anything that Piston has told you, this should look suspiciously like a cosine curve. As you will recall from our previous discussions, let me see, I think we'll do this right over here. All right, position, velocity, acceleration. Right, position, velocity, acceleration. If I throw a ball in the air, position, velocity, acceleration. Right, that should look familiar. If that doesn't look familiar, then you need to review that very seriously because that's how it works. First derivative, second derivative. Right, velocity is how fast your position is changing, and acceleration is how fast your velocity is changing. Right, it's the slope. This is the slope of that, and this is the slope of that. Okay. Coincidentally, the first derivative of my cosine is going to be my inverse sine, because, right, if my position is out here, what's my velocity? 0. Coming through here, fast negative, right? Fast negative. Where am I? Down here, right? It's flat, so coming through 0, right? It plots the change, right? Is that okay? Does that make sense? Acceleration plots this guy. So this guy at pi over 2 is flat, so 0. This guy at pi is moving pretty fast in the positive direction, so positive. This guy at 3 pi over 2 is, the slope is flat, so you're at 0, right? And then you just take the first derivative of negative sine, which looks like a negative cosine to me, although I'm pretty bad at identities. I need these graphs usually to show me what I'm doing. Okay, we're gonna call that there, and any further instructions will be where they should be. I'll catch up with you and let you know what to do.